Hi, everyone. Thanks so much for coming to my talk. I'm particularly grateful to Matt for giving me an opportunity to speak to you today about a theory which I hold very close to my heart. That is a theory of general relativity. I think it's a stunningly beautiful theory, not just mathematically, but also conceptually. And I'm excited to tell you the story of how Einstein came up with this theory today. Now, in my few years in the UK, I've learned that a lot of things, good things mostly, start here by sitting under apple trees. It's not really clear if Isaac Newton actually did sit under an apple tree. I'm sure people in Trinity College who are rightly very proud of the heritage of having hosted him there will tell you differently. And in fact, they still have a graft of an apple tree, which is apparently related to the apple tree in their garden. But what is known is that Isaac Newton came to the astonishing conclusion that the force that governs the apple falling from the tree, or any object that causes objects to fall to the ground around us, is the same force that governs the motion of celestial bodies, of planets around stars, and so on. I speak, of course, of the force of gravity. Now, in Newton's formulation, the force of gravity took on a form that was identical to the form taken by, for example, the electromagnetic force. And this means that this force would increase when the distance between the two gravitating objects was smaller. Now, Newton's theory of gravity, and in addition to this, he had obviously formulated his very famous three laws of motion, are immensely successful. They weren't just successful then, they're successful now. In fact, most people do not need to use in their day-to-day experience of the world any kind of physics beyond Newtonian physics. So all, if not most, if not all engineering applications are dependent upon Newtonian physics. And Newtonian gravity governs how the maths of how rockets are propelled into outer space. So the question is, why do we need anything different beyond gravity? Well, in my day-to-day experience as a cosmologist, somehow Newtonian gravity doesn't quite cut it. Now, this infographic is an infographic of the history of the universe, as we know it so far. I'm interested in the extreme left-hand side of this picture, that is a very early universe. And events such as the Big Bang cannot really be explained within the paradigm of Newtonian gravity. On the extreme right of the picture, which is where we are in time in the history of the universe, we see that the universe is expanding in an accelerated way. And this is probably due to some sort of component that we know very little about, called dark energy, which causes this accelerated expansion. But these concepts of geometry accelerating and being dynamic, or even trying to understand why we live in an accelerated expanding universe, is beyond the scope of Newtonian gravity as well. So as a cosmologist, it is very important for me to have a hold on other theories of gravity that could probably help me understand how the history of the universe has unfolded. We can also take an example slightly closer to home, in fact, within our very own solar system. That is the case of Mercury. Now, when Mercury revolves around the sun, it is the planet closest to the sun, of course. At the point in its orbit when it is closest to the sun, that is at its periapsis, or in the case of Mercury, since it is around the sun, the perihelion, the orbit, the plane in which the revolving orbit rests, actually also rotates. And this rotation of this plane of this orbit is called precession. Now, the precession of Mercury is something that cannot really be explained with the Newtonian physics. And when people had noticed this at the time, before Einstein had come up with his theory of general relativity, it was attributed to limited computing power. It's funny because there are so many things today in physics that we also attribute to limited computing power, and perhaps we're all just waiting for a paradigm shift to happen again. But essentially, Newtonian physics, despite its simplicity, excuse me, despite its simplicity, I'm having a bit of a glitch, so bear with me. We're back. The point is that Newtonian physics, despite its simplicity, is very difficult to solve when the number of gravitating objects within it is up to 3. So the three-body problem can't really be solved analytically. And in our solar system, we definitely have more than 3 objects. And this was the reason that people thought there was a discrepancy in explaining the precession of Mercury's orbit. The interesting thing is that Einstein's theory of general relativity, when he proposed it, was able to explain this precession to a degree of a very high degree of accuracy. Before we can go into that, let's go back to basics a little bit, and let's try to understand space and time in Newton's world and the concept of relativity, which existed way before Einstein did, back up to when Galileo was propounding his version of Galilean relativity. So with this, we start with the concept of a frame of reference. A frame of reference is just a frame that you as an observer, the person who's doing the experiment, erects. So for example, right now I'm sitting in my couch and I am talking to you and I am at rest. Now, if I were to go for a walk, people in my flat would look outside and see me walking and realize that my frame of reference was in motion with respect to them. So no frame of reference can be an absolute rest or an absolute motion, sort of. And everything and rest and motion are concepts that have to be talked about relative to a particular frame of reference. So in this picture, the black lines denote a frame of reference, which is at rest with respect to the blue frame of reference, which is in motion. And the blue frame of reference is moving with a velocity v. Now, any object within the blue frame of reference will have to vector add this velocity v to any other object that they might observe outside their frame of reference. So for example, if there were to be an object that would be moving with some velocity v prime in the black frame of reference, then the person in the blue frame of reference would observe their velocity to be v prime vector added to v. Great. Now, if we know that this is how relative velocities are computed, the question then arises that if the object moving in the blue frame of reference, not the black one this time, was not just a ball that you throw up, but was actually light, say you shone a flashlight, then it would seem that the velocity of light would change depending upon which frame of reference you were in, and moreover, could keep increasing and with no bound on how much it could increase until. But this concept was in direct contradiction to Maxwell's theory of electromagnetism, where the speed of light was seen to be a constant, and this constant parameter, which was also finite, entered into these equations. So it seemed that the only way that you could resolve this discrepancy was by hypothesizing that there was some universal frame of rest where the speed of light was the finite parameter value that was fed into Maxwell's equations. Now, this frame of rest at the time was hypothesized to be the ether, and people generally believed in this ether frame of reference until two experimentalists, Michelson and Morley, engineered their experiment to show that the existence of the ether was in fact null and void. At this point, to resolve this crisis in theoretical physics, Einstein entered with his theory of special relativity. To understand special relativity, I invite you to consider this thought experiment with me. Let us say that you and your friend are standing in a train on opposite ends of the train. I am standing in between the two of you, exactly in between, at the very midpoint. And the two of you decide to throw a ping pong ball at me. You decide to throw this ping pong ball at exactly the same instant. So if the ping pong ball is traveling equal distances to reach me, which it must do because I'm standing at the exact midpoint, and if you and your friend together have managed to throw the ping pong ball at exactly the same instance, then it stands to reason that the ping pong balls from both of you will reach me at exactly the same instant. That is, you throwing the ping pong ball will be simultaneous to me receiving, I will simultaneously receive both ping pong balls from both you and your friend. Now let's think about the situation when the train starts moving. If the train starts moving in a particular direction, in this diagram, it is moving towards my right, then it stands to reason that the ping pong ball that is being thrown by the person standing in the direction of motion has to travel a longer distance to reach the denoted midpoint than the person who was throwing the ping pong ball from the opposite end. Therefore, the simultaneity of both ping pong balls reaching reaching the person in the middle changes. And the simultaneity changes with respect to whether the frame of reference, which in our case is the train, is at rest or is in a state of uniform motion. Now, this is really interesting because simultaneity being relative to the state of motion means that the way we measure time, or the way we measure time intervals, will in fact depend upon what state of motion the frame of reference we are measuring this time interval is in. Ultimately, if you think about it, the way you measure a time interval is through simultaneity. You look at your watch, the hands on your watch are the flashing display. That event is simultaneous to an event that occurred for you to want to check the time. And this goes on. So in general, it is seen that in the case of uniform motion, within the context of special relativity, time intervals are dilated. Now, we said that we wanted to keep the speed of light a constant. If the distance is equal to the speed of light multiplied by the time interval, and the speed of light has to be a constant, then a dilation of the time interval would imply a contraction of the length interval. And this is all seen by considering the fact that the ping pong balls that are being thrown by you and your friend towards me travel with a finite speed. Now replace ping pong ball with a flashlight, and you will see that exactly the same sort of situation arises if we consider that light also, like the ping pong ball, will travel at a finite speed, as was hypothesized by Maxwell. Now let me ask you another question, and I'm going to ask you to do another thought experiment with me. If you are in a rocket, think of a rocket as a metal box. You have taken a magic pill, which means that you do not require oxygen to breathe, and there is no air around you. Therefore, you are experiencing no air resistance. Your rocket engines have failed, and you have no communication with the outside world, so you haven't panicked yet, and you do not know that you are on your way, freely falling towards a very, very gory death. Then is there any way for you to know whether you are freely falling towards your demise or whether you are floating out in space? And the answer is there isn't. So anybody who is freely falling under a uniform gravitational field, which the Earth's gravitational field is not, but for the sake of argument, we shall assume this, will not be able to tell the difference between whether they are falling under a uniform gravitational field or they are floating out in space where there is no gravitational field. This is a restricted statement of something called the equivalence principle, and I'm going to try to extend it. What I am going to say is that A person sitting in this metal box with no air resistance whatsoever and no communication with the outside, when at rest in a uniform gravitational field, can drop objects, like let go of an apple if you like, and the apple will fall to the ground at the acceleration due to gravity, 9.8 meters per second squared. They have no way of telling the difference between them being at rest in this uniform gravitational field or them being accelerated upwards with an acceleration which is uniform and is equal to the acceleration due to gravity. The only way they could tell the difference is if the mass parameter that controlled how fast or how much force or how much acceleration they would feel was different. And the difference between the gravitational mass, which determines how fast an apple would fall under gravity, and the inertial mass, which determines how fast the apple would fall if the rocket box thing that you were in was being accelerated upwards with the same value of acceleration, were unequal. And the discrepancy between these two is very, very small. So far, we have two ways of understanding Einstein's equivalence principle. We have seen that freely falling observers in a uniform gravitational field can't detect the gravitational field, and for them, the situation is identical to freely falling, if you like, in outer space. And observers cannot distinguish between being at rest in a uniform gravitational field and being uniformly accelerated in the opposite direction. So, for example, if, as we have said, if somebody at rest in a metal box lets go of an apple, the apple will fall. In a similar way, somebody being accelerated uniformly in the opposite direction shines a light beam transverse to their direction of motion. The light beam will not follow a straight trajectory, but will instead fall under gravity because the light itself can't tell the difference between an upward uniform acceleration and being at rest in a gravitational field. We can extend this analogy further for the case of clocks, and we will measure time intervals in a similar way to how we had measured this before. Let us now assume that at the top of this metal box, your friend is standing and is sending a signal down to you when you are at the bottom of this metal box. Now, because both of you are in this metal box, which is at rest in this uniform gravitational field, the situation is identical to you being accelerated upwards with a uniform acceleration. Therefore, the amount of time that it will take for a signal from your friend at the top of the box to reach you at the bottom of the box will in fact become longer. So this means that the time interval is in fact being dilated. So this is why we say that gravitational time dilation takes place and clocks in a gravitational field tend to run slower. So this means that depending on what kind of gravitational potential you find yourself at, and this is just a fancy way of saying where you are positioned in the gravitational field. For example, your friend was positioned at a height. You might find that the way you measure time is going to be different. So what are we really getting at here? We've just seen that depending on where you are in a gravitational field, you measure time differently. Clocks tend to run slower. And the question is that we can ask, why is this? Now, it could be there's something intrinsic about gravity that interferes with the way clocks run at a particular height, which causes them to run slower. But this sort of argument is not dissimilar to people who try to deny the fact that the Earth is curved, flat earthers, if you like, trying to say that clocks run differently in different places on Earth. For example, pilots are well aware that it takes longer to fly from Lagos to Bogota than from Paris to Montreal. Now, we all know that this is because of the curvature of the surface of the Earth. And in a similar vein, Einstein was able to come to the conclusion that if we consider space and time as one entity, and we understand that in the presence of matter, the space and time is also curved, we can explain the dilation of this time interval, among other things. So ultimately, we come to the crux of the matter in the theory of general relativity, where space-time is an object and an entity together in itself, and it has a geometry. And this geometry is curved, and the way it is curved is dictated by the matter content, objects such as planets, stars, you, me, anything that has mass that exists within the space-time. In turn, the curvature of the space-time is a surface which tells these objects how to move along these surfaces. So ultimately, the problem of understanding how things move under gravity, it reduces to a problem of understanding the geometry of space-time. And this is exactly the formalism that Einstein has used and that we all use now to do work within the field of general relativity. Now, since we've understood a little bit about how space-time can bend, let me give you a quick example of seeing this in practice. Now, say as an astronomer on Earth, we're interested in observing an astronomical object that is quite far away. The trouble is there is another object that we're not that interested in observing, which is much bigger than the object we are interested in between us in our line of sight. Now, because this object is quite big, it has quite a large effect on the geometry of space-time, and it curves the geometry of space-time quite a lot. Now, as in the example which I gave you about being at rest in a gravitational field versus being uniformly accelerated and shining a light beam and the trajectory of light no longer being straight, but actually falling or bending under this gravitational field, in a similar way, we can see that the light or the signal that the object we're interested in emits comes to us on a bent path because of this massive object in between us and the emitting object. Now, this effect is not dissimilar to a lens of some sort coming in between us and an object of interest, and us seeing that object in a distorted way. So similarly, when we make astronomical observations, we see these objects, these astronomical objects, their images being slightly distorted by other massive objects that have come in between us within our line of sight. Now, this is not really a hassle and can actually be really informative because, for example, the gravitational lensing of the cosmic microwave background can tell us quite a lot about the large-scale structure and distribution of galaxies in our universe, which are in effect lensing the cosmic microwave background. This lensing phenomena also leads us to seeing another massive object that we don't know very much about. So when we see a lensing effect like the one I'm showing you here from something that does not show up on optical telescopes, then we have to assume that there is some entity there which is very massive, and therefore interacting with space and time and causing it to curve and causing it to lens, but one that does not interact with light. Hence is born the concept of dark matter. It is massive, but it is dark because it doesn't interact with light. Also, we don't know a lot about it. Now, the question is dark matter a completely new form of matter that we are yet unable to detect? Or is there some sort of discrepancy in the way we understand gravity, or within the paradigm of general relativity or outside? Some people say even by modifying Newtonian dynamics that we have to do in order to understand why these objects get lensed in this way. Of course, then the question I have asked in the beginning of the talk arises, then why is the universe expanding in an accelerated manner? A late time acceleration can possibly be explained by some mysterious concept known as dark energy. Given its name, we already know that it's dark, so we don't know very much about it. We don't really have a microscopic model to understand it. Einstein, by force, had tried to put a term which he called the cosmological constant to build a static universe in his mind. And this cosmological constant, ironically, might be a very simple model for dark energy for a definitely non-static universe, a universe that is expanding in an accelerated way. But whatever model we choose, we don't really know what causes this accelerated expansion. And the point may be that this accelerated expansion is caused by us either not understanding the distribution of matter in our universe today, or it can be caused by us not really understanding the nature of gravity as a whole and us having to go beyond general relativity. Now, I've spent a little bit of time telling you about why general relativity doesn't work, but overall, it is a beautiful theory and it is very, very successful to the point that we have not been able to prove it wrong so far. And one of the biggest examples is the example of gravitational waves. So in 2016, LIGO, a project that was designed to detect gravitational waves and harness them for the purpose of gravitational wave astronomy, was able to detect something quite amazing. They were able to detect the ripples in space-time geometry that were caused by a merger event of two black holes of the order of about 30 solar masses, that is 30 times the mass of the sun, that happened 1.6 billion light years away from the Earth. So when these two objects collided, this collision set off a very energetic event, which caused space-time to bend and curve, and not just that, actually ripple in the form of waves. Now, Einstein's theory of gravity had predicted the form of these waves down to the dot that was picked up by the LIGO team. And also it was seen that these waves are propagating at very, very close, vanishingly close to the speed of light, which means that these waves, if they were carried by some particle manifestation, such as a graviton, would be carried by a nearly massless graviton, much like the photon. So there's a lot of information that we can extract from gravitational waves, but the main takeaway from this is that it was a resounding smoking gun test or verification of Einstein's theory of general relativity. With that in mind, the task of modifying gravity is a highly non-trivial one. This is a slide I took from Dr. Sarikakis' talk. And there you can see that the program of modifying gravity is a very, very involved one. And people have made fantastic progress in creating these models by modifying everything from the field content, from changing how gravity relates to matter, from trying to incorporate higher dimensions and understanding the effects of these higher dimensions on our 4 dimensions, trying to build non-local theories, add complexities in the theories through higher order theories, and the list goes on. It is an exhaustive list, and model building efforts in this area have been spectacular. But despite all of this, there is no one theory that is without reproach and which can actually fit all of the issues that I have described in this talk. And for this reason, the search continues. And for myself, I have chosen the universe as my testing ground, my laboratory for these various theories of gravity. But there is room for more ideas. We are, I believe, on the brink of yet another paradigm shift in theoretical physics. And I invite all of you to be part of this very exciting phase that we are all going through right now. And anyway, thank you so much for coming to my talk. And with this, I think I will end.